Hello friends, in this video I'd like to solve the following problem from the Greek International Mathematical Olympiad Team Selection Test 2020, problem number 1. We wish to find all functions f from the set of positive real numbers into itself, such that f of y times f of z plus f of z times f of x plus f of x times f of y equals yz plus zx plus xy for all positive numbers x, y, and z. It's a very nice functional equation, a bit complicated. Here are my hints, which I will follow. So we have the following. First, set x, y, and z to be the same to find f of x times f of x. In particular, you should be able to find f of 1. Then, multiply the formula for f of x times f of x, multiply it by x times f of x, and apply function f on both sides of this equation. That should allow you to find f of 1, to find just f of 1, right? And then set z to be 1 in our original equation, then set x to be 1, and express f of y in terms of f of y and z. And crucially, to produce some type of symmetry, change x to f of x in our condition, which I marked previously by this pink dot. And notice the symmetry going on the left-hand side. Finally, use this symmetry, set y to be 2 to show that our function must be affine. So give this problem a try, and I will see you in just a minute. Right, so let's mark this equation asterisk, and now let's start with setting x, y, and z to be the same in our condition asterisk. Then we have the following. On the left hand side we'll have 3 times f of x times f of x equals 3x squared, which after division becomes f of x times f of x equals x squared. And let's mark this condition by double asterisk. Let's mark it by 2 asterisks. In particular, for x equals 1, we have f of 1 is 1. Alright. And now, what I wish to do is to take again this equation. So from equation which I marked double asterisk, I can write the following. Follow me. So originally we have f of x times f of x, and that equals x squared. And now I will multiply both sides of this equation by x times f of x. And finally, I will do one more thing. I will apply function f on both sides. Now, notice the nice thing. Here we have f of something times f of something. By our condition double asterisk, the entire left-hand side can be simplified just to x times f of x squared. And that equals f of x cubed times f of x. I have used here, this part is by double asterisks. Alright, and in particular, set x to be 1. Set x to be 1, and we get the following. On the left hand side we have f of 1 squared equals f of 1 but f of 1 is 1. We can take square root because we are dealing with positive numbers. And we get that f of 1 must be equal 1. Right. Now, let's set z to be 1 in our very first functional equation asterisk. Then we have the following. We have f of y times f of 1 plus f of x plus f of x times f of y equals x plus, or rather y times z, but y times z is just y, zx is x plus xy. Very well. Now, crucially, f of 1, we have established it's 1. So we have, after some shuffling, f of x plus f of y plus f of x times f of y, that equals x plus y plus xy. It is very important. This equation is very important. I will mark it, I will circle it, and I will mark it triangle. Why not? Triangle, condition triangle. Now, set x to be 1 in this condition triangle. Then we have the following. On the left hand side, we have f of 1 plus f of y plus f of y equals 1 plus y plus y. And now let's do some simplification. f of 1 is just 1. So this is 1, and that cancels with this number 1. And we can derive the following formula. F of y equals 2 times y minus f of y, which I will mark, this condition I will mark square. And now, using condition square in our previous equation, so using square in condition triangle, well, here we have f of x, but f of x can be replaced by 2x minus f of x. Then we have plus f of y plus f of x, f of y, and that equals x plus y plus xy. Now I can do the following. I can write it as minus f of x plus f of y plus f of x, f of y equals, I can subtract 2x, I have minus x plus y plus xy. Now, crucially, let's change x to f of x in our previous equation. Why? Because we wish to make this expression symmetric with respect to x and y. And we can do exactly that by changing x to f of x. And now we have the following. Minus f of x plus f of y plus f of x, f of y equals minus f of x plus y times f of x. And now let's use our condition, which I marked by square once again. F of x can be replaced, or minus f of x can be replaced by minus 2x plus f of x by our condition square. And now I need a new page, so give me a minute. right? So we have the following. We can also put this 2x on the right-hand side, and we have f of x plus f of y plus f of x f of y equals 2x plus y times f of x minus f of x minus f of x. Now, crucially, we have produced a symmetric expression of the left-hand side. So the left-hand side is symmetric with respect to x and y. So I can change x to y and y to x. So I have the following: 2x plus y times f of x minus f of x. I can change x and y, so I have 2y plus x f of y minus f of y. And now, crucially, let's set y to be equal to. Let's set y equal to. Then we have the following: 2x plus 2 f of x minus f of x equals 4 plus x plus f of 2 times x minus f of 2. And now on the left hand side we will have f of x, and let's put everything else on the right hand side. We have f of 2 times x plus x minus 2 times x. So it's f of 2 minus 1 times x, and here we have minus f of 2 minus 2. So it's minus f of 2 minus f of 2. Sorry, I probably have made a small mistake. I have probably made a small mistake. Let me verify it. No, I haven't. No, I haven't. Sorry, because here I have plus 4. Now it's all well and good. So we have plus 2 minus f of 2. Now it's all well and good. So we see that our function is affine. Our function is affine. F is affine, i.e. f of x equals ax plus b, because this is a constant as well. For some constants a and b. Now, the rest of my reasoning will be, now comes the easy part. We will just find a and b. Well, you can directly plug it in our functional equation, but I wish to do it in a different way. Along the way, we have established that f of 1 is 1. So, since f of 1 is 1, well, here we have 1, a plus b. So, a plus b equals 1, which means that b equals 1 minus a, which means that our function f of x equals ax minus a plus 1. Alright, now we have to find our second variable, and now let's use the condition which I have proven at the very beginning, namely this condition double asterisk. F of x times f of x equals x squared. So since f of x times f of x equals x squared, we have the following. Well, on the left hand side we have f of x ax minus a plus 1 equals x squared. So f of ax squared minus ax plus x equals x squared. And now let's apply f again. A times this minus a plus 1 equals this. And now let's multiply, and let's put this x squared on the left hand side. We will have a squared minus 1 times a squared minus a squared x plus x, so plus 1 minus a squared times x. And finally, we have plus 1 minus a equals 0 for every positive number. For every positive number x, and that can only be true if a equals 1, because every term must vanish. So that means that a must be equal 1, which means that our function f of x equals, let's go back, ax minus a plus 1. If a is 1, our function is just f of x equals x for all positive numbers x. And now, to finish our problem, let's do verification. Let's do verification. Well, on the left hand side, we have f of, maybe let's write it in white, f of y times f of z plus f of z times f of x plus f of x times f of y. Well, it's just yz plus zx plus xy, which happens to be on the right hand side. So it's all well and good. Our functional equation has one and only one solution, the identity function. And that is it. It was a very nice problem. I have enjoyed solving it very, very much. And I hope that you've learned something new this time. You have enjoyed my video as well. And yes, thank you very much for watching. I will see you next time. Goodbye.